I'm going to do a demo. It's called Oscillations in a Trough. I have a trough here, and I'm going to put different shapes here, and as the shapes roll down and back up, they're going to make simple harmonic motions, and they're going to oscillate back and forth. I'm going to time how long it takes this to oscillate, and then I'm going to compare to the theoretical prediction as predicted by the equations. So now let's measure the radius of curvature of the trough, right? Because this trough represents a big circle, and the center of the circle is somewhere here, so I want to calculate the radius of curvature. In order to do that, I'm going to have to calculate the distance from one side to the other side of the trough, like this distance. Okay, if you remember in the optics demonstration, I had a similar kind of thing for a diverging lens, and I measured the distance from one end to the other end. After I measure that distance, if I divide that in half, I'm going to call that B, and then I measure the distance from the straight line here to the diverging lens surface that I called A. I'm going to do the same thing here. I'm going to measure the distance from end to end using a ruler. It's from the 4 centimeter line all the way to the 95 centimeter line, so 91 centimeters. 91 centimeters, so that's 0.91 meters, right? So 0.91 meters, and then if you divide that in half, then that's going to be 0.455. 0.455 meters. That one is the value that I'm calling B, right? And then now let's calculate, let's measure the distance from the straight line to the surface of the trough. Okay, that's 9.5 centimeters. 9.5 centimeters, which is going to be, well, let's first calculate it in centimeters, and then we can change our result to meters. So let's say, keep this in 45.5 centimeters. Okay, if you remember from that diverging lens equation, the radius of curvature, okay, R from the center of the circle to here, that's R, and then from here to here, that's going to be R also. So then if I subtract, this is, I'm calling this piece here A, so then this is going to be R minus A, and this I'm calling B. So we have R squared is equal to R minus A quantity squared plus B squared. Okay, so then I'm going to square this R squared minus 2RA plus A squared plus B squared, and then the R squared cancel, and then 2RA is equal to A squared plus B squared, and then R is equal to A squared plus B squared over 2A. Okay, so let's calculate what that is. My A is equal to 9.5 centimeters, and then I'm going to square that, and then the B is equal to 45.5 centimeters. Then I'm going to square that, and then divide by 2, and then A, 9.5 centimeters. So let's calculate that. This big R, that's the radius of the trough. I'm going to call this one big R here. So let's just label this big R. 113.7 centimeters. Now change that to meters, and it's 1.137 meters. Okay? So now I'm going to put an object there. It's going to have its own radius. So let's first put a solid sphere. Okay? Let's say a solid sphere. Okay? And then have it roll back and forth, time the period of that. The diameter is 3.8 centimeters. Diameter is 3.8 centimeters. Okay, let's have it go back and forth, oscillate, and then count 5 oscillations, and then we can divide that by the result by 5 to get the period of one oscillation. Okay? That's 1, 2, 3, 4, 5. 5 oscillations took 12.2 seconds. 12.2 seconds. So 12.20 seconds per 5 oscillations. So that's the experimental period. So let's put this here, T experimental, 2.44 seconds. Let's put the radius of the big trough, 1.137. And then let's put the radius of the ball itself. The little r is going to be the radius of the ball. What was that? This one, since it's 1.9 centimeters, right? So then convert that to meter, 0.019 meters. Okay? Now let's run it with a solid cylinder. It's bigger, so let's measure the radius of that cylinder. 7.5 centimeters is the radius. So I'll call this R equals 7.5 centimeters. Change that to meter, 0.075 meter. Right, and then we'll say this is solid cylinder. Okay, now let's run that. 1, 2, 3, 4, 5. Okay, 12.29 seconds. Okay, so we'll just round it, let's say 12.3 seconds. 12.3 seconds, so the T experimental is going to be 12.3 seconds divided by 5. How do we calculate the theoretical? What's the theoretical? So then the equations here look like this. You have a rolling object, right? So we have here the mg, its weight, and then in order for something to roll, you must have static friction force up the incline, Fs. So then those are all the forces that you have, the mg and then the friction force, right? So then what's happening here? This is the surface right here. Okay, so the object will have acceleration down the incline, right? So you're going to have here mg sine theta minus Fs is equal to ma. That's the acceleration of the object down the incline, right? Then you have a torque on the object due to the friction force, right? This is the section that we cover in chapter 10 on rolling motion. So you have the radius of the object, right, times the friction force equals to the moment of inertia of the object times its angular acceleration, right? So then, depending on what the moment of inertia, the shape of that object is, I can just put here for I, for general, right? And then the alpha is going to be the angular acceleration of the object, so it's going to be its tangential acceleration divided by the radius of the object. But then if it's rolling without slipping, the tangential acceleration is equal to the center of mass acceleration. So we have here I ACM divided by R, and then ACM is what I'm calling its acceleration down the incline, right? So I can just replace it by A. So then we can say here Fs is equal to IA over R squared, right? And then depending on what the shape is, I can put the I later on. And then I can substitute this in here, right? So then I have here mg sine theta minus IA over R squared, that's equal to ma. Right? And then I can calculate what the predicted acceleration of the object is down the incline. So then I can say here mg sine theta is equal to I over R squared plus m. Now let's more closely analyze what we have actually calculated here to try to understand the meaning of that. We have treated this problem as if it's an object on an inclined plane like this, and we have done the equations of rolling motion, right, mg and Fs, right, and we have calculated the acceleration of the center of mass, the acceleration of the center of mass of the object, right, as it's going down the incline. So that is related to the sine of the angle of the incline, right, and then also the moment of inertia of the shape. But in our case, it's actually not going down a ramp that is a constant angle, but it's going down a trough. So how are those related? In our case, we have a trough like this, right, whose angle of inclination is constantly changing. So at a particular point in time, imagine that this is on a ramp like this, right? This angle is theta, right? So we calculated, depending on where it is on the trough, if you think of the tangent line of that trough, and it makes an angle theta with respect to the horizontal, right? but that angle is going to be constantly changing. So now, in our case, what's happening is that if you visualize the center of the trough, the center of the curvature, and look at here, a line from the center of curvature to the center of the sphere, right? So we have calculated the acceleration of the center of mass of the object as it's going down, right? ACM. And that depends on the sign of the angle of the inclination. This angle and this angle are the same. The angle that the radial line from the center to the object will point, and the vertical. That theta and that theta are the same, right? So to show you, think of the simple example when the object goes to the bottom of the trough, right? And a radial line from there to there, the angle is going to be what? The theta is going to be 0, right? And then the object would be like on a horizontal line, and the theta will be 0. So sine of 0 is going to be 0, and then at that moment the acceleration of the center of mass is going to be momentarily 0, right? So you can kind of see that it makes sense. Then the line from the center to here, the angle from the vertical will also be 0. So as the object is going higher and higher and higher and higher, right, it's on a greater incline, and this angle theta is also going to get larger and larger. So this theta and this theta are the same. So now what we can say is that the center of mass acceleration, right, is equal to the distance from here to here, that's r minus r, times the alpha, times the angular acceleration, which is the rate of change of the rate of change of theta, right? In rotation, we learned that when something is rotating like this, right, this is A tangential. A tangential is going to equal the radius times alpha, and alpha is, the meaning of that is the second derivative of this angle, theta, right? It's the rate of change of the rate of change of the angle with respect to some point, right? A tangential is equal to ACM, right? The acceleration of the center of mass of this object, and it behaves like an A tangential. So in our case, the distance from the center to the center of the object is going to be r minus r. So I'm going to say A tangential is r minus r, and multiply that by alpha. So then you're going to have here mg sine theta is equal to a center of mass, which is r minus r, times I over r squared plus m times alpha. Okay. In our case, to make the sign work out a little bit better, if the acceleration ACM is positive, then the angle will actually be decreasing. So the rate of change of the angle will be negative. So I should put here a negative sign, just to be a little bit more specific. So then I can bring everything over to this left side. I can say r minus r, I over r squared plus m. This one is the rate of change of the rate of change of that, so the second derivative of theta, plus mg sine of theta. This is where usually in oscillation theory we make the small angle approximation. So we're going to assume that the angle of the object from the vertical in radians is small, so sine of the angle, theta, will approximately equal theta. So I'm going to replace this with theta. That's called the small angle approximation. Then I'm going to use the result that I have for any kind of oscillations, right, based on the spring problem. The spring and the block at the end of a spring, when it makes oscillations from the equilibrium point, right, we have negative kx equals ma, 0 equals m second derivative of x with respect to t plus kx, right? So we have shown that when you solve this differential equation, that the frequency of oscillations has the following radial frequency, k over m, and then the period is 2 pi m over k. So as long as your differential equation can be modeled like this, some constant times the second derivative of a function plus another constant times the function is 0, right? So then our period theoretical is going to be 2 pi square root of, and then m is going to be whatever is in front of the second derivative, right? So it's going to be r minus I I over r squared plus m, right? So r minus r, I over r squared plus m. Then you divide that by mg. So this could be the general equation for the theoretical period made by any oscillating object of any shape and any radius, right? I could even have a big basketball and do this with the basketball, right? So then you're going to have here the big R at 1.137 minus the little r, which is going to be 0.019. Okay, the moment of inertia, well, in the case of a solid sphere, the moment of inertia of a solid sphere is 2/5 mr squared. 2/5 mr squared. Then I'm going to divide that by r squared, right? And then plus the mass of the object divided by m times g. Now notice what happens, the mass of the object will cancel and the radius of the object will actually cancel too, because I'm dividing the moment of inertia of the object over the r squared, right? So that when you actually calculate this, you're going to have t theoretical is going to be 2 pi 1.137 minus 0.019. So the r squared cancels the r squared. 2/5 plus 1, that's going to be 7/5. And then the m will cancel the bottom m. So all you need is the ratio, the 7/5 ratio, which is 1.4, right? So then you're going to have here 9.8. So now let's put all this in, let's calculate it. Our result was very close, 2.44, right? So that's actually really good. So we can get the percent error from that. 100% times 2.51 minus 2.44 over 2.51. Okay, really good result. Okay, so then how about for the solid cylinder? The solid cylinder has a bigger radius, so its radius is going to affect the result more. For the sphere, this radius wasn't too large, right? So then the solid cylinder is going to be what? Put the radius of the cylinder 0.075. Okay, and then what's the difference? Instead of 2/5 mr squared, the moment of inertia of a solid cylinder is half mr squared. 1/2. Okay, but everything else is the same. The r squares cancel, the m's cancel. Then you have a half plus a 1, which is going to be 3/2. So the only thing that's changing between the shapes is this ratio is becoming a different number. Instead of 7/5 right now, it is 3/2, which is 1.5, and then of course the radius of the object is being changed here. So then you have here 0.075. So let's see what this one comes out. 0.53 seconds. So what ended up happening, even though the radius of the cylinder was larger, the ratio that we got here, 3/2 is 1.5, versus for solid sphere the ratio was 1.4. Remember, the ratio was 7/5, which is 1.4. So this became larger, this became smaller, so the theoretical period didn't change a lot. It went from 2.51 to 2.53, right? And then when we conducted it, the experimental period went from 2.44 to 2.46. So the experimental period went up a little bit, the theoretical period went up a little bit too. So we're going to get a very similar error. So 2.77% error. Okay, what if I do a bigger ball whose radius affects the results more? One, 2, 3, 4, 5. The radius of the basketball is 11.8 centimeters. So it's a bigger ball, but it's a hollow sphere. So I have to take that into account too. So how do we adjust this? So we put here, convert that to meters, 0.118. 0.118. The moment of inertia of a hollow sphere is 2/3 mr squared. So 2/3. And then of course everything cancels. 2/3 plus 1 is going to be 5/3. 5/3, and then here it's going to change to 0.118. So even though this number is going to be less, the ratio of 5/3 is going to be 1.67, right? So it's going to be a bigger ratio than the when it was a solid cylinder, which was a 1.5, right? So that might change it also. So let's put everything in. 2.61 seconds, okay? Of course, the timing too, I'm only doing it once. In a real laboratory setting, we would do this timing over and over and over again, make sure that our times are consistent, and then take the average of that time. So you can see from these three examples here, I had a solid sphere, I had a solid cylinder, and a hollow sphere. How to do these kind of oscillation problems. You first solve it like a rolling motion, right? And then you relate it to the angle of the trough. Then you use the small angle approximation, and